talking about precipitation hardening. Generally, it's in the syllabus of aluminium alloys, but it actually happens, precipitation hardening, to 3 different families of alloys in the syllabus. Steels. The precipitation hardening treatment involves soaking the metal to form a uniform phase, cooling it quickly to trap that uniform phase as a metastable phase, and then giving it a heat treatment to allow precipitates to form throughout the metal. That is tempering of martensite. Formation of quench-hardened steel, tempering martensite. In aluminium alloys, it's formation of a single-phase alloy, followed by a little bit of heat to produce precipitation of aluminium-based compounds through the metal. And the third one it happens to is copper beryllium. It's in telecommunications. And what it actually does is the copper beryllium precipitates throughout the metal and hardens copper to a point where it behaves as a spring. It's used in electrical contacts because of copper's high conductivity. It's also used in mining tools because it's very hard and copper does not spark. Last thing you want when you're underground in a coal mine is to be making sparks and setting fire to coal dust. The explosions you hear about in other countries are usually due to sparks happening underground. Copper beryllium is used in coal mines to avoid sparking. It's used in telecommunications for switchgear. So, precipitation hardening, you dissolve the solute in the base metal, cool it rapidly and you get that metastable phase. So the red dots are the solute. They don't want to exist like that, but because you've cooled quickly, they're trapped. You apply a small amount of heat then, and the precipitates form locally. It's called optimally aged. The precipitates actually make a strain field. You can see I've drawn it in here, throw over to HD. You can see I've got crosses for atoms, and I've gone and made a precipitate that's slightly bigger, but it still keeps coherency with the lattice. It makes massive strain fields, which produces time at temperature, strength. Optimally aged gives you maximum strength because it's interfering most of all with atomic motion. If you heat it up more, then what you get is you just get globs of precipitates that are just sitting in an island of something else, or they're an island in another matrix. There's not that local strain field to the same extent, so that means it's not as strong. And optimally overaged materials, overaging, that's overaging, reduces strength. Optimally aged is maximum interference with atomic motion. As quenched is low strength because it's just a soft, solid solution hardened material. Could be steel, could be aluminium, could be copper beryllium.